Welcome to this lecture on transition metal organometallic chemistry from principles to applications. In our last lecture, we discussed about transition metal sigma aryl complexes, particularly with respect to their stability, which arise due to the interaction of transition metal with aryl ligand. And what we had observed that the two interactions which are crucial to transition metal organometallic complexes, which are these ligand to transition metal sigma interaction and transition metal to ligand pi back donation is very crucial to bring about the stability of transition metal aryl complexes. And what we had seen that the influence of transition metal to ligand sigma pi back donation causes extra stability to transition metal aryl complexes with regard to transition metal sigma alkyl complexes. So, this extra stability results in higher bond energy of transition metal aryl bond and also subsequently higher decomposition temperatures, and we had seen that with respect to titanium tetraphenyl that decomposes above 0 degree centigrade, whereas titanium tetramethyl decomposes at minus 40 degree centigrade. In our discussion, we had also seen how this transition metal to ligand pi interaction brings kinetic stability to bis-mesityl metal PR3 whole 2 type square planar complexes. And that was explained by this transition metal to ligand pi interaction occurring between this ligand pi star orbital So, this is transition metal to ligand pi star orbital that brings about stability to transition metal aryl complexes. So, with that we saw that these transition metal aryl complexes are somewhat more stable than transition metal sigma alkyl complexes. Now, today we are going to see another very interesting application of transition metal aryl complexes with regard to the formation of metallo benzenes. And metallo benzenes are an important class of molecules in which the metal itself is a part of the benzene frameworks, and this is a very interesting applications of transition metal aryl complexes. In metallo benzenes, where the metal is part of a benzene ring. And the metallo benzene has been prepared for osmium in the reaction PPH3 whole 3 osmium COCS in presence of C2H2 acetylene methyl iodide, giving this metallo benzene complexes of osmium having a SMe substituent with 2 PPH3 and 1 CO and iodide ligands. So, this benzene with a metal which is osmium occupying vertices of the benzene ring is called osmabenzene. So, these metallobenzenes are similar to organic benzene in with regard to they being planar, aromatic, displaying equal bond lengths and also showing downfield enamel shifts. So, osmabenzene is planar, aromatic, exhibit equal carbon-carbon bond length, downfield signal in proton NMR, 1H resonance. For benzene it comes at around 7. So, similar downfield resonance of these protons, ring protons. And undergoes electrophilic aromatic substitution. So, this is an important application or of metal aryl compounds, whereby inorganic analog of the very famous organic molecule benzene can be prepared, and these metallobenzene can also exhibit parallel activity similar to that the real organic benzene in terms of being planar, aromatic, displaying equal bond lengths, carbon-carbon bond lengths, also showing downfield shifts for the ring proton, and finally exhibit similar electrophilic aromatic substitution reaction as shown by real benzene. So, with that we conclude our discussion on transition metal aryl complexes, which has been going on in the last 2 lectures, and now we are going to move on to another very exciting class of transition metal sigma complexes, and these are transition metal sigma alkyne complexes. These transition metal alkenyl complexes are complexes with ligands of the type there is a alkyne bond, triple bond, and these ligands are isoelectronic with cyanide, carbon monoxide, nitrogen, and these transition metal alkynyl complexes mirrors transition metal cyanide complexes with respect to color and magnetic properties, and the alkenyl ligand is strongly basic with regard to the isoelectronic ligand carbon monoxide as well as RCN, and undergoes hydrolytic cleavage. So, these transition metal alkenyl complexes undergo ready hydrolysis. So, one has to be extremely careful while preparing these complexes to protect it from water and subsequent hydrolysis that it may undergo in water. These transition metal alkenyl complexes are prepared in ammonia, solvent by following the following reaction: K3CrCN6 plus 6 sodium acetylide in liquid ammonia minus 40 degree centigrade, giving K3CrCH whole 6 plus 6 NaCN. So, care must be taken in handling these compounds, because these acetylide compounds are explosive in nature, and their order of thermal stability depends on aryl acetylide, being more stable than HC acetylide, which in turn is more stable than RC2N alkyl acetylide. Now, if one looks at this series, it is very obvious that this is more electron rich, owing to the alkyl substituents. As a result, these compounds are more reactive and less stable, whereas the aryl groups, being sp2 hybridized, can siphon off some of the electron density from the acetylide moiety onto the aryl ring, and therefore, these compounds are relatively less electron rich and hence they are more stable. Now, because of this exceptional electron richness of this alkenyl ligands with so many pi electrons or pi bonds being around it, transition metal alkenyl complexes tend to be polymeric in nature, interacting with the transition metal, where these pi clouds interact directly with transition metal. So, transition metal alkenyl complexes are polymeric and this is primarily because of their electron rich nature. So, that they tend to bind more to metal ions through polymerization, and in their polymeric form they are more stable to hydrolysis. But still are explosive. So, they usually form complexes with copper 1, silver 1 and gold 1. These metals are also called carbophilic because they have special preference for forming complexes with this acetylide type of moiety. Here is an example of the formation of a copper acetylide complex, which starts with copper iodide, where copper is in +1 oxidation state that reacts with potassium acetylide to give copper acetylide, which above 45 degrees centigrade gives Cu2C2 plus acetylene plus 2 Ki. Now, further interaction of copper with alkenyl ligand give coordination number 3. Coordination number 3 to copper, and that is illustrated by example over here. For example, here is a copper acetylide. Now, this copper interacts with the pi bond of another acetylide moiety, and this pi bond now interacts with another copper acetylide moiety. So, what is seen over here, that such kind of interaction leads to polymeric structure. Of this compound, as was discussed over here. And another important aspect to note, that these acetylide complexes are mainly formed of gold 1, copper 1, silver 1, which are late transition metal and also are electron rich. As a result, they can form these acetylide complexes and the stabilize acetylized complexes via transition metal to ligand pi back donation, which is required for stabilizing these transition metal alkynyl kind of complexes. And because of their extreme basicity of these acetylide moieties, they stabilize themselves by polymerizing and binding to several metal centers as shown over here, and thereby gaining some stability arising out of this reactivity of the acetylide moiety. Similar to copper, gold also forms gold acetylide complexes, and an example of the preparation of gold alkaline complexes is provided below. AuCl3 in aqueous medium reacts with SO2 KBr, giving AuBr2 minus, where gold is got reduced from +3 to +1, and then it reacts with acetylene in presence of sodium acetate to give this polymeric gold acetylide complex. Now, this gold acetylide complex is polymeric in nature, and the polymeric structure can be broken by addition of a dative ligand like PPH3 to give this monomeric gold triphenylphosphine CR acetylide complex, and this can be shown over here that this becomes monomeric, and the structure of the polymeric gold acetylide is shown over here for a particular example, 2-butyl C gold interacting with C-butyl gold. Now, each of these triple bond interacts with gold C-butyl, and that interacts with another C-butyl, and this interacts with this. So, what one gets is a polymeric structure as mentioned here, and which the polymeric framework can be broken by treatment with PPH3 as shown over here. Now, what is obvious over here that this polymeric framework stabilizes the exceptional reactivity of extremely basic acetylide moiety, which become very susceptible to hydrolysis, and this stabilization is gained through polymerization. Another aspect which come to the fore is that the metal has to be in low oxidation state, as in gold 1 over here as opposed to gold 3 over here for stabilizing this acetylide moiety, and this stabilization thus arises from the transition metal to ligand pi back donation, and this back donation arises because of low oxidation state of the transition metal, but preferably late transition metal which are electron rich. Now, let me summarize the topics that has been discussed in this lecture. We have looked into an interesting transition metal sigma Aryl complex in terms of the osma benzene or metallo benzene, where metal is part of the benzene ring. This metallo benzene display parallel activity similar to that of benzene in many respects and mirror the organic molecule benzene in many respects, particularly with respect to their planarity, their aromaticity, the downfield shift of the proton resonance, their aromatic electrophilic substitution reaction, so on and so forth. We have also looked into these transition metal alkynyl complexes, particularly with regard to their stability and synthetic protocols, and what we have seen is that transition metal alkynyl complexes are mainly formed of late transition metals, mainly gold, copper, silver, that too in their low oxidation state of +1, and these complexes are polymeric in nature, and their polymeric framework can be broken by addition of dative ligands like PPH3, as we have observed in case of this gold, as well as in case of the copper example that we had discussed in the previous slide. So, with that, let me conclude today's lecture on metal alkynyl complexes. We are going to discuss some more examples of metal alkynyl complexes from the perspective of their utility, synthesis, stability and their applications, and I look forward to being with you in the next lecture. Thank you.